Hello, my friend. Welcome to this journey into the hidden structure of matter, the world of particle physics. In this video, we'll gently guide you through the mysteries of the universe at its smallest scales. It's designed to be clear and calming, so you can relax, drift off, or simply enjoy learning while your mind unwinds. Let's begin. Chapter 1. What is particle physics? A map of the invisible. Particle physics is the scientific discipline devoted to uncovering the most fundamental structure of matter and the forces that act upon it. It is sometimes called high-energy physics because the deeper we probe into nature, the more energy is required to reveal its smallest parts. At its core, particle physics asks a question that has been with humanity since the earliest philosophers wondered about the nature of substance. What lies beneath everything we see? Where do solidity, form, and interaction ultimately come from? Unlike classical physics, which deals with everyday scales of motion, or nuclear physics, which studies the atomic nucleus, particle physics is concerned with constituents so small and so elusive that they cannot be seen directly, even with the most powerful optical instruments. To reveal them, scientists rely on indirect evidence, scattering experiments, collision debris, and patterns of decay. The objects themselves exist at scales smaller than a trillionth of a meter, and in many cases survive for less than a millionth of a billionth of a second before transforming into something else. Understanding such entities requires both extraordinary technology and a willingness to trust inference drawn from statistical signatures in data. The central insight of particle physics is that the world around us is built from a surprisingly small number of basic ingredients. What appear to us as solid and continuous, a table, a mountain, or a star, is, at the deepest level, a collection of particles interacting through fundamental forces. Those interactions govern why atoms form, why nuclei bind, why the sun produces energy, and why matter clumps together to form galaxies. The achievement of particle physics has been to show that such a vast range of phenomena can be reduced to a single framework of particles and interactions. The path to this understanding began with atoms. For centuries, the atom was thought to be indivisible, a final unit of matter. In the early 20th century, experiments showed otherwise. Rutherford's gold foil experiment revealed that atoms contain tiny, dense nuclei surrounded by clouds of electrons. Soon after, it became clear that nuclei themselves were built of protons and neutrons. For a time, it seemed that the proton, neutron, and electron were the ultimate building blocks. But further investigation revealed that even protons and neutrons are composite objects made of smaller entities called quarks, bound together by particles known as gluons. The picture became richer still with the recognition of other families of particles, leptons, including the elusive neutrinos, and bosons that carry forces. To study these particles, scientists had to invent machines capable of reaching unprecedented energies. Accelerators became the laboratories of the invisible. By propelling beams of particles close to the speed of light and colliding them, physicists recreated conditions that existed in the earliest moments of the universe. In those fleeting instants, energy transformed into new particles according to Einstein's relation between mass and energy. These particles decayed almost immediately, but detectors surrounding the collision points captured their traces. The curved paths of charged particles, the showers of energy deposited in calorimeters, the faint signals of muons escaping through layers of shielding. From these patterns, researchers inferred the presence of particles that could never be seen directly. The discoveries made with these instruments accumulated into a framework now known as the Standard Model of Particle Physics. This model organizes the basic matter particles, quarks and leptons, and the carriers of forces, photons, gluons, W and Z bosons, and the Higgs boson, into a coherent structure. It explains nearly all known laboratory phenomena with remarkable precision. Predictions made decades ago have been confirmed to astonishing accuracy, from the masses of particles to the rates at which they decay. The discovery of the Higgs boson in 2012 was a landmark moment because it confirmed the mechanism by which particles acquire mass. The Higgs field, present throughout space, interacts with certain particles and slows their motion, making them behave as if they have inertia. Without this field, many particles would remain massless. Atoms would not form, and the universe as we know it would not exist. And yet, even the Standard Model is not the final story. It leaves open profound questions. It does not explain dark matter, the invisible substance that outweighs ordinary matter in the cosmos. It cannot account for dark energy, which drives the accelerated expansion of the universe. It does not incorporate gravity in a quantum description. Neutrinos, once thought to be massless, are now known to possess tiny masses, but their values are unexplained by the model. These gaps remind us that particle physics is a map still being drawn, with large unexplored regions beyond its present boundaries. The way particle physicists build this map is worth emphasizing. They do not see particles in the way one sees an image under a microscope. Instead, they interpret events statistically. If a new particle exists, its presence will change the likelihood of certain outcomes in collisions. It may appear as a small excess of events at a specific energy, or as a distinctive combination of decay products. These patterns emerge only after millions or even billions of collisions have been recorded and analyzed. The confirmation of the Higgs boson, for example, required comparing data from two enormous detectors, ATLAS and CMS, each staffed by thousands of scientists. The evidence appeared not as a picture of the particle itself, but as a bump in a graph representing the frequency of certain decays. To accept such findings, physicists rely on rigorous statistical standards, demanding that the probability of a fluctuation mimicking the signal be less than 1 in several million. The history of particle physics is also a story of ideas tested against nature. In the 1930s and 1940s, cosmic ray experiments revealed a surprising zoo of new particles, far more than expected. The situation was chaotic until theorists proposed the Quark model, suggesting that many of these particles were not fundamental but combinations of a smaller set of building blocks. Deep inelastic scattering experiments later confirmed the existence of quarks. Similarly, the unification of electromagnetic and weak interactions into the electroweak theory predicted the W and Z bosons, which were subsequently discovered at CERN in the 1980s. Time and again, theoretical proposals guided experiments, and experimental discoveries reshaped theory. The field thrives on this interplay. Equally important is the scale of collaboration. Modern particle physics experiments involve thousands of researchers from around the world. Detectors are so complex that no single scientist could understand every detail. International teams design, build, and operate them, sharing costs and expertise. Scientific papers often carry author lists that stretch for pages, reflecting the reality that progress depends on cooperative effort. This culture of openness, peer review, and cross-checking has become one of the hallmarks of the field. Although particle physics may seem remote from daily life, its influence extends widely. The technologies developed for accelerators and detectors have led to advances in medical imaging, radiation therapy, superconducting magnets, and computing. The World Wide Web itself was invented at CERN as a tool for sharing data. Beyond technology, the methods of particle physics, careful measurement, statistical rigor, and collaborative verification have shaped the way science is practiced more broadly. But the deepest reason particle physics captivates us is not technological utility. It is curiosity. To ask what matter is made of is to ask about ourselves, for we too are built from these hidden constituents. To measure their interactions is to understand why the universe has taken its present form. The early universe was a particle physicist's laboratory on a cosmic scale, with energies far beyond any machine on Earth. By recreating even a fraction of those conditions, we glimpse the processes that set the stage for galaxies, stars, planets, and life. As an opening chapter, this is not the place to explore every detail of quarks, leptons, bosons, or experimental methods. Those subjects will unfold gradually in later chapters. For now, it is enough to understand what particle physics is, a science that probes the invisible, that seeks to reduce the complexity of the universe to its simplest ingredients, and that uses both imagination and machinery to do so. It is a field that has already revealed profound truths, yet still leaves some of the greatest mysteries unsolved. Perhaps the most humbling reflection is this: everything that seems familiar and solid is, at its foundation, a restless dance of particles, flickering into and out of existence in accordance with mathematical laws. The same matter that forms our hands, our thoughts, and our instruments also forms the stars and galaxies. In mapping the invisible world, we are, in a quiet way, mapping ourselves. The quest is both scientific and existential, to know what the universe is made of, and in doing so, to know what we are. Chapter 2. From Atoms to Protons and Neutrons. The story of particle physics begins not with quarks or leptons, but with the atom itself. The word atom comes from the Greek atomos, meaning indivisible. For the philosophers of antiquity, atoms were imagined as the ultimate units of matter, tiny and unbreakable. For more than 2,000 years, this idea remained in the realm of philosophy rather than science. It was not until the 19th century that chemists and physicists began to provide evidence that matter really is composed of discrete units. John Dalton, in the early 1800s, proposed his atomic theory, which suggested that each chemical element is made of identical atoms, and that chemical reactions are rearrangements of these atoms. Dalton's idea explained the regularity of chemical reactions and the way elements combine in fixed proportions. Although atoms were still invisible, the theory gave them scientific standing. Later in the century, the discovery of the periodic table by Dmitri Mendeleev reinforced the concept. The repeating patterns of chemical behavior could be understood if the elements were arranged by atomic weight, hinting that something deeply systematic lay behind the properties of matter. The first direct experimental evidence that atoms were real came from the study of electricity in gases. When J.J. Thomson investigated cathode rays in the 1890s, he discovered that they consisted of negatively charged particles, far lighter than atoms. He called them corpuscles, though they are known today as electrons. This was a revolutionary finding. If atoms contained smaller constituents, then they were not indivisible after all. Thomson proposed a model in which electrons were embedded within a sphere of positive charge, like raisins in a pudding. This plum pudding model was an imaginative first step, but it would soon be challenged. The real test came in 1909, when Hans Geiger and Ernest Marsden, working under the direction of Ernest Rutherford, carried out their now famous gold foil experiment. They fired alpha particles, which are helium nuclei, at thin sheets of gold. Most passed through with little deflection, as expected if the atom were a diffuse cloud. But a few bounced back at sharp angles, something the plum pudding model could not explain. Rutherford interpreted this as evidence that atoms have tiny, dense centers of positive charge. The atom, he concluded, is mostly empty space, with nearly all its mass concentrated in a central nucleus. This discovery was a turning point, replacing philosophical speculation with experimental proof of atomic structure. The nuclear model of the atom brought new puzzles. If electrons orbited the nucleus like planets around the sun, they should radiate energy and spiral inward, collapsing the atom. The resolution came from the emerging field of quantum theory, with Niels Bohr's model showing that electrons could occupy stable energy levels without radiating continuously. While quantum mechanics would go on to explain the behavior of electrons and the chemistry of atoms, the nature of the nucleus itself remained an open question. Rutherford continued to explore this mystery. In 1919, he achieved the first artificial nuclear reaction, bombarding nitrogen gas with alpha particles and observing the emission of hydrogen nuclei. From this, he inferred that the hydrogen nucleus was a fundamental building block present in all nuclei. He named it the proton. It quickly became accepted that nuclei are composed of protons, each carrying a positive charge. But protons alone could not explain everything. For instance, helium was known to have atomic mass around 4, but only 2 units of positive charge. Something else must be present inside the nucleus to add mass without adding charge. The answer arrived in 1932, when James Chadwick discovered the neutron. By studying the radiation emitted when beryllium was bombarded with alpha particles, Chadwick found that a neutral particle with mass similar to the proton was being produced. This was the missing piece. Nuclei consist of protons and neutrons, held together by a powerful force strong enough to overcome the electrical repulsion of the protons. With this discovery, the modern picture of the atomic nucleus was established. The recognition of neutrons explained many puzzles. For one, isotopes, atoms of the same element with different masses, could now be understood as nuclei with the same number of protons, but different numbers of neutrons. It also clarified nuclear stability. Certain combinations of protons and neutrons form stable nuclei, while others are unstable and undergo radioactive decay. The neutron's neutrality allows it to act as a kind of glue inside the nucleus, moderating the repulsion between protons. Once the composition of nuclei was understood, new lines of inquiry opened. How do protons and neutrons interact? What is the nature of the force that binds them? In the 1930s, Hideki Yukawa proposed that this nuclear force is mediated by the exchange of particles, later identified as mesons. This was the first step toward the idea that forces are carried by particles, a concept that would become central to particle physics. The discovery of protons and neutrons also had profound consequences for technology. Nuclear fission, the splitting of heavy nuclei, releases enormous amounts of energy because the mass of the resulting fragments is slightly less than the mass of the original nucleus. That difference appears as energy according to Einstein's equation, and it powers both nuclear reactors and nuclear weapons. Conversely, nuclear fusion, the joining of light nuclei, powers the sun and other stars. These processes demonstrated that the nucleus is not merely a static object, but a reservoir of energy that shapes the universe itself. Understanding protons and neutrons also revealed that they are not as simple as they once seemed. Early scattering experiments in the 1950s and 1960s showed that protons and neutrons are not indivisible but contain smaller constituents. These later came to be identified as quarks. But that is a story for another chapter. For now, what matters is that the step from atoms to protons and neutrons established the idea that matter has a layered structure. Atoms contain nuclei, nuclei contain nucleons, and nucleons themselves contain something deeper. The exploration of protons and neutrons required increasingly sophisticated tools. Early experiments used radioactive sources and alpha particles. Later, particle accelerators provided beams of protons that could be controlled and studied in detail. Cloud chambers and bubble chambers allowed researchers to visualize tracks of particles as they passed through liquids or gases. Each step forward required not only better technology, but also sharper theoretical insight to interpret the results. The mutual advance of theory and experiment became the defining feature of 20th century physics. The picture of matter built on protons and neutrons also helped unify chemistry and physics. The periodic table, once a classification of elements by chemical properties, now had a deeper foundation. Each element corresponded to a nucleus with a certain number of protons. The arrangement of electrons around those nuclei explained chemical behavior, while the composition of the nucleus itself explained isotopes and stability. What had once been separate disciplines, chemistry's atoms and physics nuclei, became part of a single structure of knowledge. The nuclear model of matter also transformed our understanding of the cosmos. Stars shine because of nuclear processes. Hydrogen fuses into helium in stellar cores, releasing energy that balances gravitational collapse. In more massive stars, heavier elements are forged in successive layers, and the explosions of supernovae distribute those elements across space. Protons and neutrons, forged in the first minutes after the Big Bang, became the seeds of all later structure. Without them, there would be no stars, no planets, and no life. Even now, protons and neutrons remain central to many unsolved problems. Why are protons stable, while neutrons decay outside nuclei? Why do the strong interactions that bind them together have the peculiar properties they do? What accounts for the exact ratio of protons to neutrons in the universe? These questions drive research into the frontiers of nuclear and particle physics. They remind us that even concepts established a century ago remain fertile ground for discovery. Looking back, the journey from atoms to protons and neutrons was not just a series of experimental findings. It was a conceptual revolution. It showed that matter is not smooth and continuous, but built from nested layers of structure. Each layer revealed new rules, new forces, and new surprises. From Dalton's atomic theory to Rutherford's nucleus, from Chadwick's neutron to Yukawa's meson, the path was shaped by bold ideas tested against evidence. This chapter represents more than scientific progress. It represents a shift in perspective. The universe is not composed of indivisible lumps of substance, but of structures that can always be probed more deeply. At each level, nature reveals new patterns that were invisible at the level above. The atom gave way to the nucleus to protons and neutrons to quarks. The process is ongoing, and it is not yet clear whether it will ever reach a true endpoint. At the end of this story, a simple reflection is fitting. Everything familiar, from the air we breathe to the stars we see, is composed of protons and neutrons bound within nuclei. Their existence defines the very possibility of matter. Without them, the cosmos would be a cloud of free particles, never coalescing into worlds or beings. In studying these hidden cores, we are not just learning about physics, we are tracing the origin of ourselves. Chapter 3. The Particle Zoo, Too Many to Count. By the middle of the 20th century, physicists thought they were closing in on a simple picture of matter. Atoms had been explained as electrons orbiting compact nuclei, and nuclei themselves were made of protons and neutrons. Alongside these, neutrinos had been proposed to balance the books of nuclear reactions, and photons were well known as the carriers of light and electromagnetic force. With these particles in hand, it was tempting to believe the fundamental structure of matter had been revealed. The universe appeared to be built from just a few building blocks, elegant in their simplicity. That hope did not last. As detectors grew more powerful and new sources of data became available, physicists began to encounter a menagerie of additional particles. Some were discovered in high-energy cosmic rays striking Earth's atmosphere, others in beams produced by particle accelerators. They came with strange properties, unexpected masses, and unfamiliar lifetimes. Instead of a handful of elementary particles, there were suddenly dozens, and then hundreds. The neat picture of matter as protons, neutrons, and electrons gave way to what became known as the particle zoo. The first surprise arrived in the 1930s with the discovery of the positron. Carl Anderson, studying cosmic ray tracks in a cloud chamber, observed a particle that looked like an electron but bent in the opposite direction in a magnetic field, revealing it carried positive charge. This was the first confirmed case of antimatter, predicted by Paul Dirac's theory, but astonishing to see in reality. The positron was followed by the muon, discovered by Anderson and Seth Nettermeyer in 1936, another particle that behaved like an electron but was about 200 times heavier. Physicists joked, "Who ordered that?" because there seemed to be no need for such a particle in the structure of matter. The muon did not fit into the neat framework of protons, neutrons, and electrons. More surprises followed in rapid succession. Pions or pi mesons were discovered in cosmic rays in the late 1940s. Their existence had been anticipated by Hideki Yukawa, who had proposed that the nuclear force between protons and neutrons was carried by an intermediate particle. Pions seemed to play exactly that role, confirming Yukawa's idea and providing the first evidence that forces themselves might be mediated by particles. Yet soon, other mesons were discovered that did not fit this explanation. Kaons, for example, appeared in cosmic ray experiments in the 1940s. They had unexpected properties, decaying in ways that violated the patterns known from other particles. Physicists began to speak of strange behavior, and eventually the term strangeness became a formal label for a new quantum property. By the 1950s, accelerators were reaching energies high enough to create particles not normally produced in cosmic rays. Bubble chambers, filled with superheated liquids, allowed researchers to photograph the tracks of particles as they ionized atoms along their paths. These pictures revealed events of stunning complexity. A single collision could produce a shower of new tracks, spiraling and branching in multiple directions. By analyzing the geometry of these tracks, their curvature in magnetic fields, and their endpoints where decays occurred, physicists identified an ever-growing array of particles. It soon became clear that the list of elementary particles was far longer than anyone had imagined. In addition to protons, neutrons, electrons, and neutrinos, there were mesons, hyperons, and resonances with fleeting lifetimes. Some lived for billionths of a second, others only for trillionths. Each discovery seemed to demand a new name, a new entry in the growing catalog. By the late 1950s, dozens of different baryons and mesons were known, each with its own mass, charge, and decay pattern. The number continued to climb into the hundreds. This proliferation of particles created a crisis of understanding. If fundamental physics was supposed to reveal simplicity, why did nature present such complexity? Were all these particles truly elementary, or were they composite in some hidden way? The analogy often made was to chemistry before the periodic table. Chemists once faced a bewildering collection of elements, but order emerged when Mendeleev arranged them into a system that revealed patterns and pointed to deeper principles. Particle physicists suspected something similar was at play. The zoo might not be random, it might reflect an underlying structure. Amid the flood of discoveries, a few patterns stood out. Families of particles appeared that seemed related by shared properties, such as spin or electric charge. Multiplets, as they were called, suggested that particles were not isolated but members of larger groups. The concept of symmetry became increasingly important. Just as crystals in solid-state physics are shaped by the symmetries of their atoms, particles seem to be organized by abstract mathematical symmetries. One striking case was the behavior of strange particles. They were produced readily in high-energy collisions but decayed relatively slowly, an odd combination. To explain this, Murray Gell-Mann and Kazuhiko Nishijima introduced a new conserved quantity, strangeness, in the 1950s. By assigning this label to particles, they could make sense of the rules governing their creation and decay. This was an early sign that the zoo could be tamed by systematic classification. Still, the situation remained unsatisfying. The muon, the pion, the kaon, and the many hyperons could be listed and measured, but what tied them together? What principle explained why so many existed? Some physicists argued that the zoo was a temporary problem that would vanish as experiments improved. Others believed it pointed to a deeper layer of structure waiting to be uncovered. The growing catalog also raised practical challenges. Each new particle discovery required careful analysis, often by teams poring over thousands of bubble chamber photographs. Graduate students became adept at tracing the paths of spirals and forks, determining where decays had occurred and what masses the parent particles must have had. Conferences became dominated by discussions of new states, new decays, and new symbols to describe them. By the early 1960s, the particle zoo had become a symbol of both progress and frustration. Progress because so much new information had been uncovered, frustration because no unifying principle yet explained it. The zoo was not limited to mesons and baryons. New leptons also entered the picture. The muon's existence demanded an associated neutrino, which was confirmed experimentally in 1962. Later, even heavier leptons would appear, such as the tau discovered in the 1970s. Each new addition deepened the sense that the structure of matter was more elaborate than originally thought. The abundance of resonances, extremely short-lived states that decayed in fractions of a trillionth of a second, added further complexity. They hinted that the strong nuclear force had many possible ways of binding particles together, creating a spectrum of states much like the excited levels of atoms. But unlike atomic levels, these resonances were themselves unstable particles, each deserving a name and classification. By the end of the 1950s, particle physicists had reached a paradoxical moment. They had more data than ever before, but less clarity about what it all meant. The zoo was real, and it was vast. Yet beneath the confusion, glimmers of order were beginning to appear. Group theory, a branch of mathematics dealing with symmetries, offered a way to classify particles into families. Gell-Mann and Yuval Neeman independently proposed what became known as the Eightfold Way, a symmetry scheme that organized many of the zoo's particles into coherent groups. This was a powerful hint that the proliferation of states might be explained by a smaller number of building blocks, much as the chemical elements are explained by protons, neutrons, and electrons. The Eightfold Way would eventually lead directly to the Quark model, but at the stage of the particle zoo, the key point was the recognition that chaos could hide deeper simplicity. The zoo was not an embarrassment. It was the raw material from which a new framework could be built. Without the painstaking cataloging of mesons, baryons, and resonances, the deeper order would have remained invisible. Looking back, the era of the particle zoo illustrates an essential feature of science. Progress is not always neat. Sometimes the pursuit of simplicity first reveals overwhelming complexity. The discovery of hundreds of particles was not a mistake, but a necessary step. Each new track in a bubble chamber, each new resonance on a graph, was a clue. The zoo forced physicists to confront the limits of their assumptions and pushed them to invent new theories capable of making sense of the data. From today's perspective, it is clear that the zoo was a symptom of substructure. Protons and neutrons, once thought elementary, are themselves made of quarks. The myriad mesons and baryons are simply different combinations of quarks bound together by the strong force. But in the 1950s and early 1960s, that picture had not yet crystallized. All that was visible was the bewildering variety, a reminder that nature rarely gives up its secrets easily. As the chapter of the zoo closed and the chapter of quarks began, physics transitioned from classification to explanation. But the zoo era remains a vital lesson in humility. It shows how science advances not only through elegant theories, but also through the hard, patient work of sorting through complexity. And perhaps there is an existential thought to carry forward. The universe, when examined closely, is not always simple. It can appear chaotic, overflowing with detail, yet hidden within that complexity are patterns waiting to be recognized. In the swirling tracks of particles, as in the events of our own lives, what looks at first like confusion may conceal a deeper order. Chapter 4. The Quark Model, Bringing Order to the Chaos. By the early 1960s, particle physics was drowning in discoveries. Dozens of mesons and baryons had been catalogued, each with its own mass, lifetime, and peculiar decay modes. Conferences filled with reports of new states, some lasting billionths of a second, others existing only as fleeting resonances in collisions. The particle zoo had grown so vast that many physicists worried the search for simplicity had gone astray. Nature was supposed to be economical, but here it seemed to multiply entities without limit. Amid this confusion, a few bold thinkers proposed that the proliferation of particles might be an illusion. Perhaps the zoo was not a true reflection of fundamental reality, but a sign that hadrons, the collective name for protons, neutrons, and other strongly interacting particles, were not elementary at all. Instead, they could be composites built from smaller, more fundamental pieces. If that were true, then the bewildering variety of mesons and baryons might reduce to a smaller set of building blocks, much like the multitude of molecules in chemistry reduces to a few types of atoms. The first step toward this idea came through the application of symmetry. In mathematics and physics, symmetry is a powerful tool for organizing complexity. Murray Gell-Mann in the United States and Yuval Neeman in Israel independently applied group theory, a mathematical framework for classifying objects by their transformations, to the hadrons. They noticed that many of the known baryons and mesons could be arranged into families according to shared properties like electric charge and strangeness. These arrangements, called multiplets, were not random. They followed patterns predicted by a mathematical structure known as SU3 symmetry. This symmetry scheme became known as the Eightfold Way, a name Gell-Mann borrowed playfully from Buddhist philosophy. The Eightfold Way classified mesons and baryons into organized groups of 8 or 10 members, with each member corresponding to a real particle. The power of the scheme was not only in tidying up the zoo, but also in predicting the existence of particles that had not yet been observed. One such prediction was a baryon called the omega-, with specific mass and quantum numbers. In 1964, the omega- was indeed discovered at Brookhaven National Laboratory, exactly where the theory said it should be. The Eightfold Way was vindicated and symmetry had shown its strength. But symmetry alone was not enough. The question remained, why did the hadrons fall into these families? What were the constituents that gave rise to these patterns? Here the quark model entered. In 1964, almost simultaneously, Murray Gell-Mann and George Zweig proposed that hadrons were made from more fundamental particles, which Gell-Mann named quarks and Zweig called aces. The initial model postulated 3 types or flavors of quark: up and strange. Different combinations of these 3 could account for all the known baryons and mesons. The rules were simple but revolutionary. Baryons, such as the proton and neutron, were combinations of 3 quarks. Mesons were combinations of a quark and an antiquark. With just these ingredients, the hundreds of hadrons in the zoo could be explained as different arrangements, much like letters of an alphabet form countless words. The proton, for example, was made of 2 up quarks and 1 down quark. The neutron was 1 up and 2 down quarks. Kaons and pions could be explained as quark-antiquark pairs. The strange properties of kaons and hyperons, so puzzling before, made sense when one included the strange quark. The quark model immediately reduced complexity. Instead of each hadron being fundamental, they were understood as composites of a smaller set of constituents. This was a profound conceptual shift. The zoo was not a jungle without order, but an ecosystem built from a few hidden species. Initially, however, the idea of quarks was met with skepticism. No one had ever seen a quark directly. Moreover, Gell-Mann himself presented them cautiously, describing quarks as perhaps only mathematical entities that might not exist as physical particles. Many physicists treated the quark model as a convenient bookkeeping device, a way to classify hadrons without necessarily committing to the reality of quarks. The absence of free quarks in nature was troubling. If quarks were real, why were they always confined inside hadrons and never observed in isolation? The first strong evidence for quarks as real particles came in the late 1960s at the Stanford Linear Accelerator Center, SLAC. In deep inelastic scattering experiments, electrons were fired at protons at very high energies. The way the electrons scattered revealed that the proton contained smaller, point-like constituents. These constituents carried fractional charges, just as the quark model predicted. The experiments were interpreted as direct confirmation that quarks were not just mathematical fictions, but real entities inside protons and neutrons. This was a watershed moment. The quark model had moved from a classification scheme to a physical reality. As further experiments accumulated, more flavors of quarks were discovered. The charm quark was proposed in the 1970s to explain certain patterns in weak decays and it was discovered experimentally in 1974 with the detection of the J-Psi particle, a meson composed of a charm quark and its antiquark. This event, often called the November Revolution, cemented the reality of quarks in the eyes of the physics community. Later came the bottom and top quarks, completing the set of 6 flavors we recognize today. The acceptance of quarks also resolved the puzzle of why free quarks had never been seen. The property responsible is called confinement. Quarks are bound so tightly by the strong nuclear force that they cannot exist independently under normal conditions. Instead, they are always confined in groups that form hadrons. The theory that describes this, quantum chromodynamics, QCD, emerged in the 1970s and explained how gluons act as carriers of the strong force binding quarks together. The Quark model not only explained existing particles, but also predicted new ones. The spectrum of mesons and baryons could be understood in terms of different quark combinations, and experiments confirmed these predictions one after another. The once chaotic particle zoo became a structured menagerie, with its members understood as bound states of a few fundamental constituents. Beyond classification, the Quark model provided a language for describing interactions. Weak decays could be analyzed in terms of quark transitions, explaining phenomena such as beta decay in nuclear processes. Strong interactions could be understood as gluons reshuffling quarks within hadrons. Even the matter-antimatter imbalance in the universe could be studied through the subtle differences in how quarks and antiquarks behave. Looking back, the elegance of the Quark model is striking. From chaos, it brought simplicity. From hundreds of particles, it distilled a handful of building blocks. It transformed particle physics from cataloging into explanation, allowing physicists to focus on the dynamics of a few constituents rather than the bewildering variety of the zoo. Yet the Quark model also left open profound questions. Why are there 6 flavors of quarks? Why do their masses span such a wide range, from the light-up quark to the extraordinarily heavy top quark? Why are quarks confined, and could they ever be freed in extreme conditions such as the early universe or inside neutron stars? These questions remain active areas of research. The legacy of the Quark model is not just in what it explained, but in how it reshaped the practice of physics. It showed the power of bold ideas, the importance of mathematical symmetry, and the value of collaboration between theory and experiment. It turned a period of confusion into a springboard for deeper understanding. And there is a quiet existential echo in this story. What appeared as chaos, a zoo without pattern, was in fact the surface expression of a hidden order. The bewildering variety of particles was only the language of deeper simplicity. In this way, the Quark model is more than a theory of matter. It is a reminder that beneath complexity, nature often hides a profound elegance waiting for us to notice. Chapter 5. Leptons, the other half of matter. If quarks provided the key to bringing order to the particle zoo, leptons represent the quieter but equally essential half of matter. They do not participate in the strong nuclear force, and so they do not form the complicated bound states that fill the world of hadrons. Yet without leptons, the universe as we know it would not exist. The structure of atoms, the stability of matter, and the balance of fundamental interactions all depend on these light, elusive particles. The most familiar lepton is the electron. Discovered at the end of the 19th century by J.J. Thomson, it was the first subatomic particle identified. Its negative charge and tiny mass compared with atoms made it the natural candidate for the glue that holds electrons around nuclei. With Niels Bohr's model of quantized orbits and later the full machinery of quantum mechanics, the electron became the foundation of chemistry and condensed matter physics. In some sense, the electron was the beginning of particle physics itself, the first time matter was revealed to be divisible into smaller parts. Electrons, however, were only the start. In 1936, Carl Anderson and Seth Nettermeyer, while studying cosmic rays, discovered the muon. It behaved like an electron but was more than 200 times heavier. This was a shock to physicists of the time. The muon did not seem to play any role in atoms or nuclei. It was too unstable to be part of ordinary matter, decaying within microseconds into lighter particles. The physicist I.I. Rabi famously quipped, "Who ordered that?" The muon seemed superfluous, a heavier version of the electron without an obvious purpose, but nature had placed it in the spectrum nonetheless. The muon's discovery opened the door to the idea that leptons might exist in families. Later experiments confirmed this. In the 1970s, the tau lepton was discovered at the Stanford Linear Accelerator Center. Even heavier than the muon, the tau decays even more quickly, but like the electron and muon, it carries negative electric charge and interacts through the electromagnetic and weak forces. Together, these three particles, electron, muon, and tau, form a family of charged leptons, each partnered with a neutral counterpart. Those neutral partners are the neutrinos. First proposed by Wolfgang Pauli in 1930, the neutrino was an attempt to rescue the conservation laws of physics. When nuclear beta decay was studied, it appeared that energy and momentum were not being conserved. Pauli suggested that an unseen neutral particle carried away the missing energy. Enrico Fermi later developed a full theory of beta decay that included neutrinos. For decades, however, neutrinos remained hypothetical, since they interacted so weakly that they rarely left any trace. It was not until 1956 that Clyde Cowan and Frederick Rines provided direct evidence for the neutrino. Using detectors near a nuclear reactor, they observed signals consistent with antineutrinos interacting with protons, producing neutrons and positrons. This was one of the most difficult feats in experimental physics at the time, confirming the existence of a particle that could pass through light years of solid matter without interacting once. Neutrinos had moved from speculation to reality, and they quickly became central to the study of fundamental physics. Each charged lepton has an associated neutrino: the electron with the electron neutrino, the muon with the muon neutrino, and the tau with the tau neutrino. Together, these 6 particles form the lepton sector of the Standard Model. Their interactions are simpler than those of quarks, since leptons are not confined by the strong force. They are free to exist as individuals, and they play crucial roles in processes ranging from nuclear reactions in stars to particle collisions at accelerators. Neutrinos in particular have been a source of mystery. For decades, the Standard Model assumed neutrinos to be massless, consistent with the difficulty of detecting any rest energy. But starting in the late 20th century, evidence accumulated that neutrinos oscillate from one type to another as they travel. This oscillation can only happen if they have non-zero mass. Experiments in Japan, Canada, and elsewhere confirmed this beyond doubt, winning Nobel Prizes in physics. The discovery that neutrinos have mass was the first clear sign that the Standard Model is incomplete. Neutrinos also play a profound role in astrophysics. They are produced in enormous numbers in nuclear reactions inside the Sun, and their detection on Earth provides direct insight into stellar processes. In 1987, detectors captured a burst of neutrinos from a supernova in the Large Magellanic Cloud. confirming theoretical models of how stars explode. More recently, detectors like IceCube in Antarctica have observed neutrinos with energies millions of times higher than those produced in accelerators, originating from cosmic phenomena such as black holes and gamma-ray bursts. Neutrinos connect particle physics with the largest scales of the universe. The study of leptons has also driven advances in experimental technology. The electron's properties are measured to astonishing precision, providing some of the most stringent tests of quantum electrodynamics. The muon's magnetic moment, measured to extraordinary accuracy, has hinted at discrepancies with standard model predictions, suggesting possible new physics. Tau leptons, despite their short lifetimes, are studied in high-energy collisions, offering insights into weak interactions and potential windows into physics beyond current theories. In comparison with quarks, leptons might seem less exotic. Quarks generate the rich spectrum of hadrons and account for the complexity of the particle zoo. Leptons are fewer in number and interact less dramatically, but their simplicity is deceptive. Without electrons, atoms would not exist. Without neutrinos, nuclear reactions would not balance, and stars could not shine in the way they do. Without muons, we would not have the experimental clues that pointed to new symmetries and interactions. Without tau leptons, the standard model structure of three generations would lack closure. Leptons also play a central role in the weak nuclear force. In beta decay, a neutron transforms into a proton, emitting an electron and an electron antineutrino. This process not only explains radioactivity, but also underlies the reactions that power the sun. The weak forces interaction with leptons is one of the pillars of the electroweak theory, which unifies electromagnetic and weak forces into a single framework. The discovery of the W and Z bosons in the 1980s confirmed this unification, with leptons as the visible participants in weak processes. The existence of three lepton families mirrors the structure of quarks, which also come in three generations. The reasons for this parallelism remain unknown. Why 3 and not 2 or 4? Why such large differences in mass between the electron, muon, and tau? Why are neutrino masses so tiny compared to their charged partners? These unanswered questions show that even the apparently simple lepton sector conceals mysteries. Experimentally, leptons offer advantages. Because they are not bound by the strong force, their properties can be measured cleanly. This has allowed physicists to test theoretical predictions with remarkable precision. For example, the electron's magnetic moment agrees with theory to more than 10 decimal places, one of the most precise matches between theory and experiment in all of science. Deviations in the muon's magnetic moment, however, suggest that new particles or forces may be influencing lepton behavior in subtle ways. The study of leptons continues to evolve. Neutrino observatories are being built on ever larger scales, seeking to measure their properties in greater detail. Experiments aim to determine the ordering of neutrino masses, to measure whether neutrinos and antineutrinos behave differently, and to see whether neutrinos are their own antiparticles. Such discoveries could have profound implications for why matter dominates over antimatter in the universe. In the grand architecture of matter, leptons stand alongside quarks as equal partners. Quarks build the composite particles that fill the particle zoo, while leptons exist more simply, shaping the structure of atoms and carrying information across the cosmos. Together, quarks and leptons form the two halves of the standard model's matter content. Without either, the framework would be incomplete. The lepton story also reminds us of science's unpredictability. The electron, discovered more than a century ago, was expected to be unique, yet nature revealed heavier cousins. The neutrino, proposed as a desperate theoretical patch, became central to our understanding of both nuclear physics and astrophysics. The muon, once dismissed as an unnecessary oddity, is now one of the best tools for testing the Standard Model. Again and again, leptons have forced physicists to revise their expectations. Perhaps that is their most profound role, to remind us that nature's logic does not always match human intuition. The universe did not stop at one kind of lepton. It built a family of 6, arranged in 3 generations, with properties still not fully explained. This pattern hints at deeper principles we have yet to uncover, and in this, there is a quiet existential thought. We live in a universe where the simplest pieces of matter, quarks and leptons, combine to create the overwhelming complexity we see. The electron, so small it can hardly be imagined, defines the chemistry of every element. Neutrinos, nearly invisible, carry messages from the hearts of stars. The fact that something so elusive and intangible can shape galaxies and lives is a reminder that the unseen often carries the greatest weight. Chapter 6: The Carriers of Force, Exchange Particles. Matter alone cannot account for the universe. Quarks and leptons are the building blocks, but they do not exist in isolation. They interact, attract, repel, and transform. It is through interactions that atoms form, stars burn, and particles decay. The fundamental interactions of nature are not abstract concepts but real processes, transmitted through the exchange of particles. These carriers of force, known as bosons, are as essential to the Standard Model as the matter particles themselves. Without them, the cosmos would be a collection of isolated fragments, incapable of forming structure or evolving in time. The idea that forces might be transmitted by exchange particles grew gradually from the early 20th century. Classical physics described forces as continuous fields. Newton's gravity acted at a distance, and Maxwell's electromagnetism filled space with fields that influenced charges. But when quantum mechanics entered the scene, it introduced the concept that fields themselves could have quantized excitations. Just as an atom has discrete energy levels, a field can vibrate in discrete packets. Those packets behave like particles, which can be exchanged between matter particles to produce a force. The simplest and most familiar case is electromagnetism. The photon, first understood as the quantum of light, is the carrier of the electromagnetic force. A charged particle, such as an electron, is surrounded by an electromagnetic field, which can be described as the possibility of emitting and absorbing virtual photons. When 2 charged particles interact, they do so by exchanging photons. Although the photons are not observed directly in these interactions, they are virtual rather than real photons of light. Their effect is measurable in the forces we observe. This picture elegantly unites the wave nature of light with the particle picture of interactions. The photon is massless, and this fact explains why the electromagnetic force has infinite range. A photon can be exchanged between charges no matter how far apart they are. The field diminishes in strength with distance, but it never disappears entirely. The universality of electromagnetic interactions, from atomic bonds to radio waves to starlight, arises from the ubiquity of photon exchange. A second great success of the exchange particle idea came with the weak nuclear force. In the 1930s, Enrico Fermi developed a theory of beta decay, describing it as a direct interaction between particles. But the theory broke down at high energies, producing infinities. Physicists realized that a more fundamental description was needed. By the 1960s, it was proposed that the weak force, like electromagnetism, was carried by exchange particles. In this case, they would have to be massive to account for the short range of the weak interaction. This proposal became part of the electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg. It unified electromagnetism and the weak force into a single framework, predicting the existence of three massive carriers, the W-pies, W-moms, and Z-bosons. Unlike the photon, these bosons would be heavy, and that heaviness would limit the reach of the weak force. Their discovery became one of the great goals of experimental physics in the late 20th century. In 1983 at CERN, the W and Z bosons were finally observed in high-energy collisions, with masses around 80 and 91 gigaelectron volts. Their detection confirmed the electroweak theory and earned their creators the Nobel Prize. The weak interaction, carried by these bosons, is responsible for processes like beta decay, in which a neutron transforms into a proton, an electron, and an antineutrino. It is also essential to the nuclear reactions that power the sun. Without the weak force, the universe's chemistry would be drastically different. That such essential processes depend on the exchange of massive, short-lived particles is a profound example of how deeply hidden mechanisms shape the visible world. The third fundamental interaction carried by exchange particles is the strong nuclear force. This is the force that binds quarks together into protons, neutrons, and other hadrons. It also binds protons and neutrons into atomic nuclei. The carriers of the strong force are gluons. Predicted in the early 1970s as part of quantum chromodynamics, gluons act between quarks, holding them together through the property known as color charge. Unlike photons, gluons themselves carry the charge they mediate. This leads to a very different behavior. Instead of diminishing with distance, the strong force grows stronger as quarks are pulled apart. This is why quarks are confined, never seen as free particles. Attempting to separate them only creates more quarks, which immediately bind into new hadrons. This phenomenon, confinement, explains why the particle zoo contained so many composite states, while quarks themselves remained hidden. The existence of gluons was confirmed experimentally in the late 1970s. At the Petra Collider in Hamburg, researchers observed three jet events in electron-positron collisions, consistent with quark-antiquark pairs radiating a gluon. This provided direct evidence of gluons as real particles, not just theoretical constructs. With that, the last missing carrier of the strong force was secured. Completing the family of force carriers is the Higgs boson, discovered in 2012. While not a force carrier in the same sense as photons or gluons, the Higgs is the quantum excitation of a field that permeates all of space. Its role is to give mass to other particles through interaction with the field. Without it, the W and Z bosons would be massless, and the weak force would not have the properties we observe. The Higgs boson's discovery at CERN was the capstone of the Standard Model, confirming a mechanism predicted nearly half a century earlier. One more force is known in nature: gravity. In the language of quantum field theory, it too would be mediated by an exchange particle, the graviton. But unlike the other bosons, the graviton remains hypothetical. Gravity is extraordinarily weak at the particle scale, and no experiment has yet detected a graviton. Nevertheless, it fits naturally into the framework as the quantum of the gravitational field. Whether gravity can be fully unified with the other interactions is one of the deepest open questions in physics. The unifying concept in all of this is that forces are not mysterious pulls acting across space, but exchanges of quanta. Every attraction or repulsion, every transformation can be described as the emission and absorption of particles. This idea not only explains the known forces, but also provides a framework for searching for new ones. If a deviation from expected behavior is observed, it may signal the existence of an undiscovered boson carrying a force not yet known. The discovery of force carriers has always been closely tied to advances in experimental technology. The photon was revealed through the study of the photoelectric effect and quantum optics. The W and Z bosons required the construction of CERN's superproton synchrotron and detectors capable of identifying rare events amid billions of collisions. Gluons were confirmed in electron-positron colliders with unprecedented precision. The Higgs boson required the Large Hadron Collider, a 27-kilometer ring buried under the French and Swiss countryside, operating at energies never before achieved. Each step demanded decades of preparation and international collaboration. The story of exchange particles also illustrates the interplay of theory and experiment. The photon was predicted by quantum theory before it was measured in detail. The W and Z bosons were anticipated by electroweak unification before they were observed. Gluons were required by the structure of quantum chromodynamics, and their discovery came years after the theory was formulated. The Higgs boson was the longest awaited, a prediction from the 1960s, finally confirmed in 2012. In each case, mathematics led the way, but experimental confirmation gave the theories their authority. These bosons also serve as sensitive probes of new physics. Precision measurements of their properties, the mass of the W boson, the couplings of the Higgs, the behavior of gluons in jets, test the Standard Model at its limits. Any deviation could point to new interactions, undiscovered particles, or deeper layers of structure. Altogether, the carriers of force complete the Standard Model's picture of nature. Quarks and leptons make up matter. Bosons carry the forces that bind and transform them. Together they form a self-consistent framework that has withstood every experimental test so far. Yet the model is not final. Gravity awaits unification. Neutrino masses remain unexplained. Dark matter and dark energy point to forces or particles beyond the known set. The carriers of force, as complete as they seem, may be only part of a larger picture. It is striking to reflect on how invisible these carriers are in daily life, yet how central they are to existence. The light we see is made of photons. The warmth of the sun depends on W bosons in nuclear reactions. The stability of protons depends on gluons confining quarks. Even the mass of ordinary particles depends on the Higgs field. Every sensation and every structure is mediated by quanta that we cannot touch or see directly, but whose presence shapes everything. And perhaps there is an existential lesson here. Forces may appear to us as abstract pulls, intangible influences, but in the quantum world, they are carried by particles as real as matter itself. The universe is held together by exchanges, by invisible messengers, binding and transforming what would otherwise drift apart. In this sense, the hidden bosons remind us that connection is as fundamental as substance, and that without the unseen ties, the visible world could not endure. Chapter 7. The Standard Model, Physics Grand Catalogue. By the late 20th century, the bewildering discoveries of particle physics, electrons, neutrinos, muons, taus, quarks of multiple flavors, gluons, W and Z bosons, photons, and eventually the Higgs, had accumulated into something astonishing, a complete framework that could explain nearly every phenomenon observed in laboratories. This framework, known as the Standard Model, became physics' grand catalogue. It was not just a list of particles, but a theory, a set of rules that dictated how those particles interact, how they transform, and how the forces of nature arise. The Standard Model is the most successful description of fundamental physics humanity has ever created. It provides equations that can predict experimental outcomes with extraordinary precision, often to many decimal places. It explains why atoms exist, why the sun shines, why unstable particles decay in particular ways, and why energy can transform into matter and back again. It is, in effect, the periodic table of fundamental physics, an organized map of the constituents of reality and the interactions that bind them. What makes the Standard Model remarkable is its coherence. The particles fall into distinct categories, each with clear roles. Quarks form the building blocks of protons, neutrons, and all other hadrons. Leptons form the other half of matter, giving rise to electrons, muons, taus, and their neutrino partners. Force carriers, the bosons, transmit the interactions. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and the Higgs boson for mass. These pieces might have been discovered in different eras, often under chaotic circumstances, but when assembled together, they fit into a logical, interconnected structure. The elegance of the Standard Model lies in the mathematics behind it. Rather than being a patchwork of ad hoc rules, it is built from symmetry principles. At its heart are gauge symmetries, abstract but powerful constraints that dictate how particles must interact. These symmetries ensure that the laws of physics remain consistent under certain transformations, and they give rise naturally to the existence of force carriers. The photon, gluon, W, and Z bosons are not arbitrary additions. They emerge as necessary consequences of the symmetries underlying the theory. Electroweak unification is one of the crown jewels of the Standard Model. It shows that electromagnetism and the weak nuclear force are two aspects of a single interaction, split into different behaviors at low energies. At high enough energies, such as those in the early universe, they become indistinguishable. The fact that this unification was predicted mathematically and then confirmed experimentally with the discovery of the W and Z bosons is a triumph of theoretical physics. The strong interaction is equally well described. Quantum chromodynamics, the theory of quarks and gluons, fits naturally into the Standard Model, with its peculiar property of confinement at long distances and asymptotic freedom at short distances. These features, once theoretical curiosities, have been confirmed again and again in experiments probing the behavior of quarks inside protons and in the jets produced in high-energy collisions. The Higgs mechanism is another triumph. Without it, the Standard Model would predict massless W and Z bosons, in contradiction with observations. By introducing a field that permeates space and a boson associated with it, the theory explained how particles acquire mass. The discovery of the Higgs boson at CERN in 2012 was the final missing piece, a capstone achievement that confirmed the Standard Model as a comprehensive framework. But the Standard Model is not just a static catalog. It is predictive. Many of its greatest achievements came not from explaining known data, but from predicting new phenomena. The existence of the charm quark, the top quark, and the tau neutrino were all predicted before they were observed. The model also predicts the rates of countless processes, how often particles should decay in certain ways, how they should scatter, and what resonances should appear in collisions. Time and again, experiments have confirmed these predictions, often with breathtaking accuracy. One famous example is the magnetic moment of the electron. The Standard Model's predictions, incorporating effects from virtual particles and higher-order interactions, match the measured value to better than 1 part in a trillion. No other scientific theory has achieved such precision. Even tiny deviations in such measurements are treated as possible windows into new physics, because the Standard Model has proven itself so exact. The structure of the Standard Model also reflects the surprising family pattern of particles. Matter comes in 3 generations, each with a charged lepton, a neutrino, and 2 quarks. The first generation, electron, neutrino, up quark, and down quark, makes up ordinary matter. The second and third generations are heavier copies, unstable and short-lived, but their existence is required for the theory to be consistent. This duplication is one of the great mysteries. Why 3 families, and why such huge differences in mass? The Standard Model does not answer this, but it accommodates the pattern seamlessly. It is important to emphasize that the Standard Model is not simply a list of particles. It is a quantum field theory, a set of equations describing how fields interact and how excitations of those fields appear as particles. It is this theoretical foundation that allows predictions to be made and tested. The model is less like a zoological catalog and more like a set of rules that govern the dance of reality. Experiments across the world have tested the Standard Model at every turn. Particle accelerators have smashed protons together at ever higher energies, confirming the behavior of quarks and gluons. Neutrino detectors buried underground or under ice have measured oscillations consistent with physics beyond the model, but still rooted in its framework. Precision measurements of W boson masses, Higgs couplings, and rare decays have probed the model at levels of detail unimaginable to the pioneers of the field. And yet, for all its success, the Standard Model is incomplete. It does not include gravity, leaving general relativity separate from the quantum picture. It does not explain dark matter or dark energy, which dominate the universe on cosmic scales. It cannot account for the matter-antimatter asymmetry that allows our existence. It cannot explain why the masses of particles take the values they do, or why neutrinos are so light. In this sense, the Standard Model is a triumph and a puzzle at once, astonishingly accurate, yet clearly provisional. The model's incompleteness is not a weakness, but an invitation. Physicists know it cannot be the final word, but its very success provides a platform for searching beyond it. Any deviation from its predictions is treated with intense scrutiny because it could be the clue to deeper laws. This is why measurements of the muon's magnetic moment, or slight anomalies in the behavior of B mesons, attract so much attention. They may be the cracks in the Standard Model's perfection that point the way forward. What makes the Standard Model truly grand is not only its accuracy but its universality. It describes phenomena across scales, from the tiniest collisions and accelerators to the processes inside stars. It links the early universe, when energies were unimaginably high, to the laboratory table. It shows that the same set of principles governs the microcosm and shapes the cosmos. It is a theory of extraordinary reach, binding together domains of science that once seemed disconnected. Reflecting on this achievement, one cannot help but feel a sense of awe. Human beings, creatures bound to a small planet orbiting an ordinary star, have managed to construct a framework that captures the workings of the invisible world with unmatched precision. We have catalogued the pieces, mapped their interactions, and tested them in machines that recreate the conditions of the universe's earliest moments. And yet the Standard Model is not the final truth. It is a map, not the territory. Its very elegance reminds us that there may be deeper layers of order still hidden. In this sense, the Standard Model is both an end and a beginning. It marks the culmination of a century of discovery, and it points toward mysteries we have yet to solve. Perhaps that is its most existential lesson. Beneath the complexity of the world lies a hidden simplicity, a set of rules that describe everything from the flicker of light to the life of stars. But that simplicity, as profound as it is not the whole story. The Standard Model is humanity's greatest attempt to write the grammar of reality, but the universe may yet have dialects we cannot speak. The quest continues, and the catalogue is still open. Chapter 8. The Higgs Boson and the Mystery of Mass. One of the deepest puzzles in physics is mass itself. Why do particles have weight? Why does matter resist acceleration when pushed? On one level, the question seems obvious. Mass is simply a measure of how much matter something contains. But when viewed through the lens of particle physics, the question becomes much more subtle. Quarks, leptons, and bosons are not made of smaller constituents. They are fundamental. Where, then, do their masses come from? The Standard Model provides an answer, and at its center lies the Higgs field. The Higgs boson, discovered in 2012, is the manifestation of this field. Its existence solved a puzzle that had haunted theoretical physics for decades: how to explain the origin of mass while preserving the delicate symmetries that make the Standard Model work. The story of the Higgs boson is therefore not only about a particle, but about the deeper mystery of how the universe acquires structure and stability. The problem of mass became urgent in the 1960s, when theorists attempted to unify electromagnetism with the weak nuclear force. The unification required the existence of force carriers. But experiments showed that while the photon was massless, the W and Z bosons had to be massive to account for the short range of the weak interaction. This posed a dilemma. If one simply inserted mass terms into the equations, the theory collapsed, losing its consistency. Yet without masses, the theory contradicted experiment. Something had to give. The solution came from an idea known as spontaneous symmetry breaking. In condensed matter physics, it was already known that symmetries could exist in the underlying laws, but be hidden in the actual state of the system. For example, a magnetized material selects a particular direction for its magnetic field, breaking the rotational symmetry of the underlying equations. Could something similar happen in particle physics? Several groups of physicists pursued this line of thought. In 1964, François Englert and Robert Bru in Belgium, and independently Peter Higgs in the United Kingdom, published proposals for how a field could permeate space and break the symmetry in just the right way. A few months later, Gerald Guralnick, Carl Hagen, and Tom Kibble published another version of the mechanism. All these papers converged on the same idea. An invisible field filling all of space could give mass to particles that interact with it. The field would allow the W and Z bosons to be heavy while leaving the photon massless. It would also give quarks and leptons their inertial masses, explaining why electrons, protons, and neutrons have the properties we observe. This field became known as the Higgs field, and the quantum excitation of that field was the Higgs boson. The theory predicted that this boson must exist, but for decades it remained unobserved. The challenge was immense. The Higgs boson was expected to be massive and unstable, decaying into other particles almost instantly. Detecting it required colliding particles at energies high enough to create Higgs bosons and detectors sensitive enough to identify its rare signatures amid overwhelming backgrounds. From the 1970s onward, experiments searched for the Higgs. Early accelerators such as the Large Electron-Positron Collider, LEP, at CERN probed possible mass ranges but did not find it. Each search narrowed the possibilities, ruling out certain mass regions and guiding future experiments. As the decades passed, the Higgs became the missing piece of the Standard Model, the one particle predicted by theory but not yet confirmed. Physicists sometimes called it the God particle, though most disliked the term because it overstated its role and misled the public about its nature. What mattered was not divinity, but necessity. Without the Higgs mechanism, the Standard Model could not function. The quest reached its climax with the construction of the Large Hadron Collider, LHC, a 27-kilometer ring buried under the French and Swiss countryside. Protons, accelerated to energies of 7 trillion electron volts, were smashed together at nearly the speed of light. The detectors built to record these collisions, ATLAS and CMS, were among the most complex scientific instruments ever created, with thousands of physicists from around the world collaborating to design, build, and operate them. In July 2012, the breakthrough came. Both ATLAS and CMS independently reported evidence of a new particle with a mass around 125 gigaelectron volts. The signatures matched the predictions for the Higgs boson, decays into pairs of photons, into pairs of W and Z bosons, and into fermion-antifermion pairs. The announcement electrified the physics community. Decades of theory, construction, and search had culminated in the confirmation of the last missing piece of the Standard Model. The discovery of the Higgs was more than just a particle detection. It confirmed the mechanism by which particles acquire mass. The W and Z bosons, heavy as observed, owe their mass to interactions with the Higgs field. Quarks and leptons, from the electron to the top quark, acquire their diverse masses through couplings to the same field. Even the stability of atoms depends on this mechanism. If the electron had no mass, it could not bind to protons, and chemistry as we know it would be impossible. If quarks had no mass, protons and neutrons would not exist. The Higgs field is therefore not a minor detail, but a condition for the very existence of matter. After 2012, the work did not end. Detecting the Higgs boson was the beginning of a new era, measuring its properties in detail. Does it couple to particles exactly as predicted by the Standard Model? Does it interact with itself in the way the theory demands? Is there only one Higgs boson, or could there be more, as predicted by some extensions of the model? These questions continue to guide experiments at the LHC. Each new dataset refines our understanding, and so far, the Higgs has behaved precisely as expected. But physicists remain alert to any deviation, because such deviations could point to new physics beyond the Standard Model. The Higgs boson also raises profound theoretical puzzles. Its mass is surprisingly light compared to what naive calculations suggest it should be. Quantum effects should drive its mass toward enormous values, unless some delicate cancellation occurs. This is known as the hierarchy problem, and it suggests that there may be undiscovered principles or particles that stabilize the Higgs. Supersymmetry, extra dimensions, or other speculative frameworks have been proposed, but none has yet been confirmed. The Higgs may be both the end of one story and the beginning of another. There is also the question of cosmology. The Higgs field may have played a role in the evolution of the early universe. Its potential energy could have influenced inflation, the rapid expansion thought to have occurred just after the Big Bang. Some calculations even suggest that the Higgs field may not be perfectly stable, and that the universe could one day tunnel to a lower energy state. While such scenarios are speculative and distant in time, they highlight how the Higgs connects particle physics to the fate of the cosmos itself. The importance of the Higgs cannot be overstated. It is not just another particle to add to the list, but the linchpin that holds the Standard Model together. Its existence validates the mechanism of spontaneous symmetry breaking, explains why the W and Z bosons are massive, and accounts for the diversity of fermion masses. Without it, the mathematical consistency of the theory would collapse, and the physical world as we know it would not exist. Reflecting on the discovery, one is struck by the scale of human effort involved. Thousands of scientists, engineers, and technicians from around the globe worked for decades to build machines capable of producing and detecting a particle that vanishes almost as soon as it is created. The success represents not only a triumph of theory and experiment, but also of international collaboration, a demonstration of what humanity can achieve when knowledge itself is the goal. And at the heart of it all lies a mystery. Why should the universe possess such a field? Why should particles resist motion in the way they do? Why does existence come with weight, inertia, and form, rather than remaining a sea of massless fields? The Higgs boson answers the how, but not the why. Perhaps this is the existential note to leave with. Mass is not simply substance, it is relationship. The particles we are made of acquire weight only through their interaction with something unseen, a field that permeates all of space. Without that interaction, there would be no atoms, no stars, no beings to ponder the question. To know that our very solidity arises from a hidden field is to glimpse how fragile and contingent the universe is, and how extraordinary it is that we are here to understand it. Chapter 9. The puzzles that remain beyond the Standard Model. The Standard Model is a triumph of human thought. It unifies quarks, leptons, and bosons into a coherent framework and explains the outcome of experiments with extraordinary precision. And yet, for all its success, physicists know it is incomplete. Like a map that captures the outline of a continent but leaves vast regions blank, the Standard Model leaves fundamental questions unanswered. These puzzles are not minor details, but central to the universe's very existence. One of the most striking gaps is dark matter. Astronomers observing galaxies discovered that the visible matter, stars, gas, and dust, cannot account for the gravitational pull required to hold galaxies together. Spiral galaxies rotate too quickly at their edges for the observed mass to provide sufficient binding. The same discrepancy appears in clusters of galaxies, in gravitational lensing, and in the structure of the cosmic microwave background. The only consistent explanation is that most of the matter in the universe is invisible, interacting through gravity, but not through light or other known forces. This dark matter makes up about 85% of the universe's matter content, yet the Standard Model provides no suitable candidate. Neutrinos are too light and too fast-moving to account for it, and none of the known quarks or leptons fit the bill. The search for dark matter has become one of the defining quests of modern physics. Experiments deep underground attempt to detect its rare interactions with ordinary matter. Particle colliders look for its production in high-energy collisions. Astrophysical observations probe its effects on cosmic structure. Despite decades of effort, dark matter's true identity remains elusive. An even greater enigma is dark energy. In the late 1990s, astronomers measuring the expansion of the universe discovered that it is not slowing down, as gravity would suggest, but accelerating. The cause appears to be a mysterious form of energy inherent to space itself, accounting for roughly 70% of the total energy in the cosmos. The Standard Model has no explanation for this. Some interpret dark energy as a cosmological constant, a uniform energy density that fills space. Others propose it might vary with time, reflecting new fields or forces. But the magnitude of dark energy is puzzling. Theoretical estimates of the vacuum energy from quantum fields differ from observations by more than 100 orders of magnitude, the largest known discrepancy between theory and experiment in all of science. Even within the Standard Model's own territory, puzzles remain. Neutrinos, once thought to be massless, are now known to oscillate between flavors, which implies they have small but non-zero masses. The Standard Model cannot explain this. The origin of neutrino masses may require entirely new mechanisms, such as the seesaw model involving heavy, undiscovered neutrinos. Understanding these masses is not a trivial detail. Neutrinos are among the most abundant particles in the universe, and their properties could hold clues to why matter itself dominates over antimatter. That asymmetry is another deep mystery. In the aftermath of the Big Bang, matter and antimatter should have been created in equal quantities. When they meet, they annihilate into pure energy. If the universe began in perfect symmetry, all matter should have vanished in a flash of light. Yet, we live in a universe filled with matter, with only traces of antimatter. Something must have broken the balance. Experiments show that certain processes involving quarks violate CP symmetry, the combined transformation of charge and parity. But the amount of violation in the Standard Model is far too small to account for the cosmic imbalance. There must be additional sources of asymmetry, perhaps involving neutrinos or undiscovered particles. Without them, the very fact of our existence remains unexplained. Another unresolved issue is the hierarchy problem. The Higgs boson, discovered at a mass of about 125 gigaelectron volts, is far lighter than naive calculations suggest it should be. Quantum corrections to its mass tend to drive it toward enormous values, close to the Planck scale, where gravity becomes strong. To keep the Higgs light requires delicate cancellations between large contributions, an unnatural fine-tuning. Many physicists suspect that some deeper principle or new physics stabilizes the Higgs. Supersymmetry, a proposed symmetry between fermions and bosons, was one candidate, predicting partner particles that could cancel the large corrections. Extra dimensions were another idea. So far, no experimental evidence has confirmed these possibilities, leaving the hierarchy problem unresolved. The Standard Model also fails to unify all forces. Electroweak unification was a triumph, but the strong force remains separate. Grand unified theories attempt to merge the strong, weak, and electromagnetic forces into a single framework at extremely high energies. Many of these models predict that protons should eventually decay, albeit with lifetimes far longer than the age of the universe. Decades of experiments have not yet observed proton decay, setting strict limits on such theories. Still, the dream of unification persists. It is motivated not only by mathematical beauty, but also by hints from cosmology and the pattern of particle families. Whether such unification exists remains one of the central questions in physics. Gravity stands apart as the most conspicuous omission. The Standard Model describes 3 of the 4 fundamental forces with great success, but it does not include gravity. Einstein's general relativity remains the best description of gravitation, but it is a classical theory, not a quantum one. Reconciling gravity with quantum mechanics has proven extraordinarily difficult. The hypothetical graviton, the quantum carrier of gravity, has not been detected. Attempts to quantize gravity run into problems of infinities. String theory and loop quantum gravity are among the approaches that seek to bridge the gap, but none has been confirmed experimentally. Until gravity can be united with the other forces, the Standard Model cannot be the final theory. Cosmology also raises puzzles the Standard Model cannot address. The rapid inflationary expansion of the early universe, which explains the uniformity of the cosmic microwave background, likely involved new fields beyond the known ones. The matter-energy budget of the universe, dominated by dark matter and dark energy, is invisible to the Standard Model. Even the distribution of the three families of quarks and leptons, their masses, and their mixing angles remain arbitrary inputs. The model works brilliantly with the parameters it contains, but it cannot explain why those parameters take the values they do. These puzzles have motivated decades of searches for new physics. High-energy colliders have looked for supersymmetric particles, new heavy bosons, or signs of extra dimensions, but so far none has appeared. Precision measurements have been pushed to unprecedented accuracy, with only tantalizing anomalies that have yet to stand the test of time. Dark matter detectors have grown larger and more sensitive, yet no confirmed signal has been found. Neutrino experiments continue to refine our understanding, with hints of unexpected behavior but no definitive breakthrough. The sense is one of anticipation. The Standard Model works so well that any departure from it must be subtle, but those departures hold the key to deeper truths. Some physicists worry that the Standard Model's very success may be a trap. Its predictions are so accurate that deviations are hard to find. It may be that the energies required to reveal the next layer of physics are beyond the reach of current technology. The Large Hadron Collider has probed to unprecedented energies without uncovering new particles beyond the Higgs. Future colliders, such as proposed electron-positron machines or even larger proton colliders, may be necessary to push further. Whether society will invest in such projects is itself an open question, but the scientific case remains compelling. For now, the Standard Model remains both a triumph and a boundary. It tells us that nature can be described with remarkable precision, yet it leaves us staring at mysteries that touch the foundations of reality. Why is there something rather than nothing? Why does matter outweigh antimatter? What is the dark matter shaping galaxies, and what is the dark energy accelerating the cosmos? What principle sets the masses of quarks and leptons? And how can gravity, the oldest known force, be reconciled with the quantum world? Each of these puzzles points to a frontier. They remind us that science is not finished, that discovery remains ahead. They also underscore the humility required in physics. Even our most successful theory is a stepping stone, not the final word. The Standard Model maps the known, but beyond its boundaries lies the unknown, vast, silent, waiting. And here is the existential echo. The puzzles beyond the Standard Model are not abstract curiosities. They are the conditions of our existence. If the universe had been symmetric between matter and antimatter, we would not be here. If neutrinos had behaved differently, the cosmos might have evolved in another direction. If dark matter and dark energy did not shape galaxies in expansion, the night sky would be unrecognizable. The incompleteness of the Standard Model is, paradoxically, what makes us possible. And so in searching for what lies beyond, we are in a sense searching for ourselves. Chapter 10. The Future of Particle Physics. New Machines, New Frontiers. The Standard Model has given us an astonishingly accurate picture of the microscopic world. yet its very incompleteness propels the field of particle physics forward. If there are puzzles beyond its reach, dark matter, dark energy, neutrino masses, matter-antimatter asymmetry, quantum gravity, then new tools will be needed to probe them. The future of particle physics is therefore inseparable from the machines and frontiers we build to explore nature at ever greater depths. Particle physics is unique among sciences in its reliance on large-scale instruments. While a chemist can probe molecules on a lab bench and a biologist can study cells with microscopes, particle physicists must recreate the conditions of the early universe to glimpse the fundamental laws. That requires colliding particles at energies never before reached, building detectors the size of cathedrals, and coordinating collaborations that span continents. The history of the field shows that each leap in knowledge came with a leap in technology. The future will be no different. At the center of this future are colliders. The Large Hadron Collider, operating since 2008, has been the most powerful machine ever built, smashing protons together at energies of 13 trillion electron volts. Its crowning achievement was the discovery of the Higgs boson, but its mission is far from complete. The LHC has been upgraded to increase its luminosity, the number of collisions per second, in order to probe rare processes with unprecedented detail. By studying the Higgs boson's properties, measuring the couplings of quarks and leptons, and searching for subtle deviations from standard model predictions, the LHC continues to test the boundaries of our understanding. But physicists are already thinking beyond the LHC. Several proposals aim to build machines that will extend our reach further. One is the Future Circular Collider, a project envisioned at CERN that would dwarf the LHC with a circumference of 100 kilometers and energies up to 100 trillion electron volts. Such a machine could explore scales at which new physics might emerge, perhaps revealing supersymmetry, heavy dark matter candidates, or unknown forces. Another idea is the International Linear Collider, a straight accelerator stretching for tens of kilometers, designed to collide electrons and positrons with exquisite precision. Unlike proton colliders, which produce messy sprays of particles, electron-positron colliders create cleaner environments, ideal for precision measurements of the Higgs and other particles. China has also proposed its own circular collider, the CEPC, which would serve first as a Higgs factory to produce millions of Higgs bosons for study. This would allow measurements of the Higgs couplings with unprecedented accuracy, potentially revealing tiny deviations that signal physics beyond the standard model. Japan, meanwhile, has explored building the ILC as a national project with international collaboration. These proposals reflect not just scientific ambition, but global competition and cooperation, as nations weigh the costs and benefits of hosting the next flagship facility. Future machines are not limited to colliders. Neutrino experiments represent another frontier. The discovery that neutrinos have mass opened an entirely new chapter of physics, and the questions it raises remain pressing. Are neutrinos their own antiparticles? Do they violate CP symmetry in ways that could explain the dominance of matter over antimatter? What is the precise ordering of their masses? To answer these questions, experiments like DUNE in the United States and Hyper Kamiokande in Japan are under construction. These projects will fire intense beams of neutrinos across hundreds of kilometers of rock, using enormous underground detectors to record their oscillations. The results could reshape our understanding of both particle physics and cosmology. Cosmic experiments are also part of the future. Dark matter has eluded detection in accelerators, but it might reveal itself through faint interactions in underground detectors, shielded from cosmic rays. Experiments using vats of liquid xenon or argon aim to detect the tiny flashes of light produced when a dark matter particle collides with an atomic nucleus. These detectors, buried deep in mountains or mines, are reaching sensitivities where they may finally glimpse the missing mass of the universe. At the same time, astrophysical observatories are searching the skies for signals of dark matter annihilation or decay, while gravitational wave detectors open new windows onto phenomena that could involve exotic particles. Even dark energy, though far more mysterious, may become accessible to particle physics. Precision measurements of the expansion of the universe, large-scale surveys of galaxies, and new generations of space telescopes are mapping the cosmos with exquisite accuracy. While dark energy may not be directly testable in accelerators, its effects shape the largest structures of the universe, and its nature may eventually require new particles or fields beyond the standard model. The future of particle physics is therefore a future of convergence. Experiments in laboratories and observations of the cosmos are becoming increasingly intertwined. The boundaries between particle physics, astrophysics, and cosmology are blurring as questions about the smallest scales become inseparable from the largest. The same neutrinos studied in underground detectors stream from supernovae. The same dark matter candidates sought in colliders-shaped galaxies. The same Higgs field that gives particles mass may have influenced the early universe's expansion. Technological innovation will be as critical as theoretical vision. Advances in superconducting magnets, cryogenics, detector design, and computing have enabled past discoveries. The next generation will push these technologies further, perhaps in ways that spill over into society. The World Wide Web was invented at CERN to share data among physicists. Future breakthroughs in accelerator or detector technology may have equally unexpected impacts. The pursuit of fundamental knowledge has often yielded practical innovations as byproducts, a reminder that curiosity-driven science enriches the broader world. Theoretical physics will also shape the future. The puzzles of the standard model, dark matter, neutrinos, hierarchy, unification, quantum gravity, provide targets for new theories. Supersymmetry, string theory, extra dimensions, technicolor, and other frameworks offer possible extensions. Most remain untested, but the dialogue between theory and experiment will continue. Sometimes, theory leaps ahead and experiment follows, as with the Higgs. Sometimes anomalies in data guide theory toward new directions. The interplay between the two is what drives progress. It is worth remembering that the future of particle physics is not guaranteed. Building colliders the size of cities or detectors the size of skyscrapers requires political will, international collaboration, and billions of dollars in funding. As machines grow larger, the challenges become not only scientific but social and economic. Convincing societies to invest in questions that seem abstract — what is dark matter? What gives mass to neutrinos? — requires making the case that fundamental knowledge is a worthy pursuit, as much a part of human culture as art or literature. The history of science suggests that such investments pay dividends in unexpected ways, but the arguments must be made anew in each generation. Still, the drive to explore is unlikely to vanish. Humanity has always built tools to extend its senses, from the first telescopes to the largest accelerators. Each time we have looked further, we have found surprises. There is no reason to think the microscopic world has given up all its secrets. The puzzles we already know, dark matter, dark energy, neutrinos, hierarchy, unification are too pressing to ignore. And history teaches us that new puzzles will emerge, ones we cannot yet imagine. The future of particle physics will therefore be shaped by both ambition and humility. Ambition, because the questions it asks are among the deepest possible. What is the universe made of? Why does it exist in its current form? Humility, because each time we have believed we were close to the final answer, nature has revealed deeper layers. The Standard Model itself, for all its precision, is almost certainly a chapter rather than the book. Perhaps the most profound aspect of looking forward is realizing that the unknown is not an obstacle but a promise. The blank spaces beyond the Standard Model are invitations. They call on us to build new machines, devise new experiments, and stretch the limits of imagination. The answers we find may transform our understanding of the universe, or they may open even greater mysteries. Either way, the pursuit itself is what defines the field. And here lies the existential reflection. The particles and forces of the Standard Model describe the structure of matter, but they do not explain why the universe is here at all, or why we find ourselves capable of asking these questions. The search for new physics is, in one sense, the search for ourselves, for the origins of our matter, for the forces that allow atoms and stars to exist, for the patterns that make life possible. Standing on the edge of the known, peering into the unknown, particle physics embodies humanity's oldest impulse, to look beyond, to imagine more, and to step into the frontier even when we cannot see what lies ahead. Thank you for staying with me, my friend. I hope this quiet exploration of particle physics brought you both knowledge and peace. If you're still awake, you're welcome to continue the adventure by watching another video waiting for you here. And if sleep has already come, may your dreams carry you among the stars. Sweet dreams.